Hi folks, we are on the Unit 2 Day 6 lesson, and in this one we're going to be talking about projections, and there's going to be two main types of projections as well as a bit of a discussion about the angles that a vector makes with the X, Y, and Z axis at the end. So I'm probably going to break this into 3 videos depending on timing and how long I talk for. So getting into the first part of projections, we've got these two scalar and vector projections. There's not any new math or any new calculations in this lesson. We're just going to be kind of talking about how to break down a vector and consider the component of that vector that's acting along with a second vector. So again, similar to the idea of the dot product, and we're going to bring in our work with the dot product in this lesson. We want to talk about one vector as a component of another vector, or how much of one vector can be written as a component of a second vector. And this is going to be we're going to start off kind of considering this with geometric vectors, but it does work with both geometric and algebraic. So we've talked about components of vectors a lot of times before. So remember that any vector in R2 can be resolved into perpendicular components, and that's actually true of R3 as well. You could resolve it into an X and Y and Z components, the 3 different components, the I hat, J hat, and K hat, as a linear combination of those 3 vectors. But in R2, it's much easier to visualize, and we can kind of get a bit of a better diagram here that's easier to draw out and sort of understand where pieces are coming. And we know that we could add an X vector and a Y vector to get our original vector, in that the X vector would be the, missing an important piece here. So it's the magnitude of V times cos theta. And these are all magnitudes. I have to go back and change that for sure. And then in the Y component, the magnitude of the vertical component is the magnitude of V times sine theta. So that's just using our SOHCAHTOA triangles. Projections are really similar to this, but we're moving off the XY coordinate system and going to look at how it works with geometric vectors. So what we've been doing all along with the vector V and looking at the X component or the Y component, this vector X is actually the projection of V onto the X axis. It's how much of the vector V goes in the direction of the X axis. But we're going to look at it kind of more generally with vectors that are geometric vectors and not related to the coordinate grid. So this is kind of a picture of what this is like. So one vector here, the yellow one, and the black vector down here, the projection is kind of like a shadow. It's like where, if you shone a light on it, where would the shadow of the first vector go? How much of that first vector is going in the direction of the second vector? So just kind of a bit more descriptive here. So this is the vector A, and here's vector B, and this piece here, I'm going to color that in a different color. That shadow there, that's the projection of vector A onto vector B. So this here, this distance here, which looks a lot like, if we kind of hop back to this one, that looks a lot like the shadow of vector V on the x-axis. And that's what this projection is here. So it's really just taking our component vectors that we created in the x and y direction and doing that more generally with geometric vectors in R2 and then eventually in R3. We're going to do a lot of the diagrams though in R2 just because R3 is a lot more difficult to draw. So here we've got 2 vectors A and B, and they're placed tail to tail and we've got an angle theta between them. So that's vector A and that's vector B. The scalar projection of A onto B is ON. And I'm just going to use a highlighter. So from point O to point N, so it's this distance here. Okay. So this magnitude, very, very similar again to what we saw with the component vectors in the X or the Y direction. The magnitude there is going to be the magnitude of vector A times the cos theta, because this would be adjacent over hypotenuse equals cos. So it's just a rearranged from SOHCAHTOA. So we can get, this doesn't really have to be magnitude because it's not vector. It's like from point O to point N, that kind of arbitrary point in there. The problem with this is that we don't necessarily know the angle between algebraic vectors. If we had the angle between them, this is very easy to calculate. So if you have geometric vectors and you happen to know the magnitude of your vectors and the angle, this is a super easy calculation. And not surprisingly, scalar product gives a scalar answer, or a scalar projection, pardon me. So we get just a scalar as our answer there, and it's just the length of that side if we kind of created a triangle with our theta. When we're looking at these vectors with the algebraic vectors, though, we don't necessarily know what the what that angle is. That's often something that we don't know. So we know that the scalar projection of A onto B equals the magnitude of A times cos to theta. So we want to get another representation for this that doesn't involve theta. And one of the things that we've really just looked at that involved magnitudes and it involved cos thetas was the dot product, right? We can remember that we had that dot product equation, A dot B was the magnitude of A times the magnitude of B times cos theta. This is an old equation that we've been working with for a couple lessons now. So magnitude of A, magnitude of B, cos theta. I want two of those three things in my projection equation. So I want that magnitude of A, and I want the cos theta, but I don't want the magnitude of B. So I definitely want to keep that. I want to keep that, but I kind of want to get rid of magnitude of B. So what we're going to do is say that this is actually equivalent to A dot B, except that we had an extra magnitude of B in here. So I'm going to divide out the magnitude of B. So if we take a look at this, we end up kind of getting a nice easy formula to work with, because if we have these algebraic vectors, we can do dot product with two algebraic vectors very easily, and we can find the magnitude of the second vector very easily. So that's how we come up with the equation, just kind of manipulating the dot product equation, because we want two of the three parts, so we just divide out that magnitude that we don't need. And there's the formula for that. Okay. If we were looking at what the scalar projection would be it be 0? Would it be positive? Would it be negative? We can kind of look at those cases And again, I've got this graph of the cosine curve. So if the vectors are perpendicular, then the scalar projection is 0, because we know that it's magnitude of A times cos theta, or it's A dot B divided by magnitude of B. And A dot B is 0 if they're perpendicular, but that also hopefully will make sense if you've got, say there's vector B, and there's A. If these are 90 degrees, how big is the shadow of A on B? There's no shadow. It's like noon. It's 12 o'clock. The sun's right overhead. There's no shadow of that vector A. The projection is 0. Okay? The next case, if this is less than 90, then the scalar projection will be a positive number. So in here, cos is positive. We know the magnitudes are always positive. I'm just going to fit in a little diagram down here. So if we've got vector B and vector A coming from there at an acute angle, then the scalar projection is here, and it's a positive value. So the projection is in the same direction as B. So where we would draw that goes along vector B when they're placed tail to tail. If we have the second case, an obtuse angle, so bigger than 90, we know that past 90, the cosine of those obtuse angles is going to be negative. So if we had something like this, here's B, and then A would be out here. Now my projection is actually back here. So the projection is measured on the other side of B. So those are kind of our three cases. If it's 90, your projection is going to be 0 because like there's no shadow. There's no help coming from A along the direction of B. If the angle is less than 90, then A is going kind of sort of somewhere in the similar direction to B. So the projection is going to be in a positive direction. If the angle's bigger than 90 and it's an obtuse angle, then A is going not at all the same direction and the projection is negative. So I wonder, can we figure out if the scalar projection of A onto B is the same as the scalar projection of B onto A? And we're going to do a numeric example of this, but let's just kind of do a diagram first and see what our prediction is. And neither a diagram nor a numeric example is actually a proof of anything, but hopefully this will kind of convince you, and then we can look at what the actual equations are and see when and if these two things are equal. So here, remember the projection is the shadow of A onto B. So this is the projection in here. I'm gonna kind of darken that up. So from O to N. So that would be that projection. If I draw, this is the scalar projection of A onto B. Okay. Now, if I was going to take those same vectors, I'll try and draw them like as much the same as I can. and do the scalar projection of B onto A, what would happen there? Here, I would drop this down, and sometimes the scalar projection actually goes past. I think I've drawn the second A. So that green up there is the scalar projection of B onto A. So we're going to do, like I said, an example with an actual vectors and kind of do it in both directions, see if they're the same, and then we'll talk about the equation and see. But I don't think like that and that are pretty obviously different, and they do end up being different, but we'll kind of look at that from a few different angles. So the scalar projection, we've got vector u is 5, 6, 3, and vector v is 1, 4, 5. So the scalar projection of u onto v, this is going to be the two vectors dot with each other, so u dot v divided by, and it's the magnitude of the second one. So this is going to be the magnitude of v. So I'm going to calculate u dot v. Remember, we take our x coordinates and multiply them. So 5 times 1, and the y coordinates and multiply them, 6 times 4, and the z coordinates, 3 times 5. And then the magnitude of v, the square root of 1 squared plus 4 squared plus 5 squared. So here, you know what, I'm just going to maybe leave this as an exact value. So here I get 5 plus 24 plus 15. So I get 44 over, that's 41, 42, the square root of 42. So we can, I'm not going to be super picky. You could, of course, rationalize the denominator there, or reduce your radicals. I'm going to leave this exact unless they ask for a rounded off answer, because it's not a real life problem. Then we're going to do the opposite, same exact vectors, but we want to find the scalar projection of v onto u. If we're projecting onto u, then we need to divide by the magnitude of u. So it's still going to be u dot v. I suppose it would be v dot u, but we know that dot product is commutative, divided by the magnitude of u. So I think you can see kind of right away there, and that's what I was talking about looking at the equations. These two things would not be equal, right? We can see from the diagram, and we're going to see from the numeric example, but right away saying u dot v over magnitude of u, is that equal to u dot v over the magnitude of v? Probably not, unless these two magnitudes were the same. And they're not going to be in this case. So we've got the same dot product. You could just put in the actual number if you'd already calculated it elsewhere, but I'm just going to fill in all the steps for the notes. And then the magnitude of u is the square root of 5 squared plus 6 squared plus 3 squared. And this one on top, we had 44, and 9 and 36 is 45, plus 25 is root 70, I think. I hope I've done those calculations right. So again, double checking, we see that scalar projections are not commutative. The order really does matter there. Last example for scalar projections, we're going to talk about whether the scalar projection of A onto B is the same as the scalar projection of A onto K times B, if K is a real number that's not 0. So we can say that the scalar projection of A onto B, we want to prove that this equals the scalar projection of A onto KB. So I'm going to just left side, right side this. And I always want to put a G in there instead of a J. Good thing I teach math, not spelling. Okay, so here we know that this is going to be A dot B divided by the magnitude of B. I'm going to stop for there and see what we get on the other side. So this is going to be A dot KB divided by the magnitude of KB. Okay, now we know that the magnitude of this is going to actually be K times the magnitude of B. And we also know that we've got the property in the dot product where K can be taken out and we can keep those vectors. So here we can just cancel out the K's and we end up with A dot B over the magnitude of B. And I'm actually going to, we do have to actually restrict because I'm going to say K is greater than 0 because the direction matters. We would end up with a negative sign if K was negative. So I'm going to restrict that to K is greater than 0, and I think that that's probably the intention here. So again, any of these properties of magnitudes, properties of dot products, you will have to be able to do proofs, and you will be kind of asked to call upon and be able to work with those and manipulate those in order to prove properties even of kind of seemingly unrelated things. So that's it. We're going to move on to vector projections in the next video.